Okay, welcome to another day of AP Calculus. What I'm going to go ahead and have you do is work on this warm-up problem for a couple moments. Okay, for the next 15 seconds, 20 seconds, go ahead and turn and talk to your neighbor about how you arrived at the answer that you have, or what are you in the process of doing to get to an answer. Okay, keep in mind that we are going to do this from the inside out, just like we would evaluate a function that is a composite. So first we're going to worry about the limit as x approaches 2 of our inside function. So here's the graph of f. Here's x equals 2. If we drive our car along the curve, we are approaching that y-coordinate, which is 2. So now we have the limit as x approaches 2 because of this right here, of now the outside function, g of x. So now as we go to x is 2, and we drive along our curve, we're at a y value of 0. Okay. Now hopefully you were able to discuss your homework a little bit before you started this video. I did want to go over a couple problems that I anticipated maybe you had a little bit of an issue with. Please use Calc Chat as a reference, especially for your odd problems. If you want to, first of all, check your answer, which is my expectation. You are checking your answers in Calc Chat. And then if you want to look at the work too, that would be a good idea. So the first one I wanted to talk about was number 45. I anticipated that maybe not all of us remembered how to factor the difference of cubes. So first of all, remember we're always trying direct substitution. So when we try direct substitution, we get 2 cubed minus 8 all over 2 minus 2, which is 0 over 0, and that's not okay for a limit, but it is a good sign that we can do something algebraically. Okay, so the numerator here is what we call the difference of cubes. Okay, we have the difference of cubes and the sum of cubes. And so I just wanted to remind you about how we factor those. Okay, the difference of cubes and the sum of cubes both start out similarly, where we have either a minus b or a plus b. Okay, and then the next three terms or the trinomial that we're multiplying are a squared, ab, and b squared. And there's only one subtraction sign in each of these. So in this first one, we already have the subtraction sign in a minus b, so these are both addition signs. In the sum of cubes, we have an addition sign, so the next one is going to be subtraction and then addition. Okay, so these are how we factor the difference and sum of cubes. So going back to our problem, we're going to factor our numerator, x minus 2, times x squared plus 2x plus 2 squared. Okay, and good thing we are able to cross out that x minus 2, so now we can do direct substitution. We can plug in 2 for x, to get 12. Okay. The next one I wanted to look at is 62. Okay, I hope that you took my advice and changed those delta x's to h's when you did your homework. 62 was probably the more algebra intensive one, and it was an even, so it wasn't in the back of the book, so I thought maybe it would be a good idea for us to go through it together before we start into our new material. So when we have x plus h, the quantity squared, okay, you can go ahead and do x plus h times x plus h, and then take that quantity times x plus h. But remember, we did some work in pre-calculus with expanding binomials, and we used the Pascal's triangle to help us. So when we go ahead and expand out x plus h, the quantity cubed, we know our coefficients are going to be 1, 3, 3, 1. So 1x squared, cubed, oh my, plus 3x squared h plus 3xh squared plus 1 h cubed. Okay, so you can do the algebra, or you can use Pascal's triangle to help you. Okay, so then our x cubes can cancel out, and we have the limit as x approaches 0 of all of these have an h. We can factor that out. So that it can cancel with that guy. And remember, now we need to go ahead and evaluate our limit. So we're going to go ahead and have to plug 0 in for h using direct substitution. So we have 3x squared plus 3xh plus h squared. Those are going to go to 0, so we're left with just 3x squared. Okay. Okay. If you have more questions than those two, let me know, and I'd be happy to help you, either from this assignment or from our assignment before. Okay. Let's go ahead and transition then into the next part of 1.3. We're going to do a couple different things today. So yesterday we started the analytical process of limits. So we talked about the direct substitution, and then we also talked about some algebra techniques that we can use, okay? So if we have a rational, then we can do some factoring maybe to cancel some things out, or like in your homework and in our notes, if we have those rationals, then we would need to multiply by the conjugate in order to get those to cancel out somehow. Okay, so today we're going to talk about the squeeze theorem, which is something that isn't used often, but just a little bit. And then we're going to talk about some trigonometric limits. Okay, so first let's talk about the squeeze theorem. Okay, and it's a lot of words, so just bear with me, or a lot of symbols. Okay, so the squeeze theorem, and we're going to break this down. No need to worry about all the symbols. Okay, so first of all, we have three functions. F of x is going to be squeezed or sandwiched in the middle of two functions, h of x and g of x. So we have a sandwich where f of x is in between h and g for an entire interval. Okay. Now, if we know that our lower end, as x approaches c, has the limit of L, and we know that our higher end has the same limit as x approaches c, then this middle guy would also have a limit as x approaches c to be L. So let's talk about this again. And like I said, this isn't as commonly used as our other techniques, but we still need to understand it. So we have a sandwich. F of x is in between h and g. H and g both have limits as x approaches c that equal L. So since f of x is squeezed in between, it would only make sense that it would have the same limit as x approaches c. Okay, let me show you an example of how this would work. Okay, so here we have our function f, and we don't really know much about it, but we know that g is here and h is here. So notice how f is in between g and h all the time. And in question, here is c. So we know that the limit as x approaches c of g is at this hole. We know that the limit as x approaches c of h is at that hole. So whatever that y value is going to help us with the limit as x approaches c of f. Okay, so an example. We want to find the limit as x approaches 0 of x times sine of 1 over x. Okay, now I have taught you, you need to always start with direct substitution. Okay, so what happens when we actually plug in 0 to evaluate our limit? We have 0 times the sine of 1 over 0. I'm thinking this 1 over 0, that's not okay. All right, so we really don't have a good way right now to evaluate that limit. Okay, well, let me show you what the graph looks like. Okay, this is the graph of it. Okay, and if we could figure out two functions that we could squeeze in between, that'd be really cool. So this is, we're trying to figure out the limit as x approaches 0 of x times sine of 1 over x. Okay, so this purple graph right here is x times the sine of 1 over x. Okay, well, here are two functions that are coming to my mind. Here's one. Y equals absolute value of x. What do you think my second one's going to be? Y equals negative absolute value of x. So we can see that that purple squiggly function is squeezed in between the orange and the green. So let's think about these. What do we know about the limit as x approaches 0 of negative absolute value of x? We know that it's 0. What do we know about the limit as x approaches 0 of absolute value of x? We know that it's 0. So since our purple squiggly function is what I'm going to call it, is sandwiched in between these two functions, then we can say with certainty, because of the squeeze theorem, that the limit as x approaches 0 of our purple squiggly function is also 0 because of the squeeze theorem. Okay. All right, so you're going to have a couple problems in your homework about this, but like I said, this is probably going to be the analytical strategy you're going to use the least. Okay, let's go back to our direct substitution strategy, and we're going to look at some trigonometric limits first. So our direct substitution is still going to work for trigonometric limits, and this is one of the reasons why we looked at the unit circle last week. I'm hoping that you can do this without your unit circle. It will be my expectation on the quizzes and the tests, but if you need to look at it as you get back in the swing of things, that's fine. Just remember, you're not going to get it for quizzes and tests. So if I ask you for the limit as x approaches pi over 3 of the secant of pi over 3, or excuse me, of the secant of x, then I got ahead of myself. We are going to do direct substitution. So I'm really asking you, what is the secant of pi over 3? Okay. Well, we know that the secant is the reciprocal of cosine. We know the cosine of pi over 3 is 1/2. So the secant would be 2 over 1. Okay. Next, we have the limit as x approaches 5 pi over 6 of tangent of x. Same thing, we're just going to do direct substitution. And the tangent of 5 pi over 6 is negative radical 3 over 3. Okay, so these are more for you to kind of practice your unit circle calculations. Okay, but then we have a couple special rules that I need you to be able to remember. Okay, so we have two special trigonometric limits. Here they are right here. Two special trigonometric limits. Number one, the limit as x approaches 0 of sine of x over x equals 1. Next, we have the limit as x approaches 0 of 1 minus cosine of x over x, and that's always going to equal 0. Okay. Now, what I want to make sure you understand about this first limit, this orange one, we could also have the limit as x approaches 0 of x over sine of x. It can just be inverted, and it's still going to equal 1, okay? Because when we flip 1 upside down, it's still going to be 1. So this could happen either way, all right? And we need to look for consistency with the angle. So as long as the angle matches the denominator, that's still going to equal 1. What do I mean by that? Okay, look at this first example. We have the limit as x approaches 0 of sine of 2x over 2x. Okay, so this is fitting the pattern of this orange one up here. And since it fits that pattern, that the angle and the denominator match each other, then we can say, okay, this is also going to go to 1. Okay. Okay. Do you see how I drew this arrow with that 1? Anytime that I'm evaluating a limit, and maybe like I'm evaluating a piece at a time, this arrow is kind of me saying, okay, this piece of the limit goes to a particular number. So it really wouldn't be necessary right here because it's the only piece that we're evaluating, but this limit goes to 1. That's kind of what I'm doing with that arrow. Okay. Let's look at number 2. we have the limit as x approaches 0 of tangent of x over x. Okay. Well, if we try direct substitution, this numerator is going to be 0 and this denominator is going to be 0. Okay, that's not okay. We can't have 0 in the denominator, but since it's 0 over 0, that's a good sign that we can do something algebraically. Okay, or in this case, trigonometrically. All right, we know that tangent doesn't have to be written as the tangent of x. Okay, we know that tangent of x can be written as sine of x over cosine of x. Okay, well let's rearrange this so that it can be helpful to us. Okay, remember that when we are dividing a fraction, it's the same thing as multiplying by the reciprocal. Okay, so I'm just going to rearrange this so that I'm going to put sine of x and x in the same fraction, and then, whoops, that's not what I wanted to write, and then 1 over cosine in the same fraction. So multiplication is commutative, so essentially I just flip-flopped where the denominator multiplication was. Okay, how is that helpful? Well, now I have the limit as x approaches 0 of sine of x over x. And that's one of our special limits. We know that this is going to go to 1. All right, so what we can do is we have 1, and we can now use direct substitution. Okay, couple more examples and then we will be on our way. So example number 3, we have the limit as u approaches 0 of sine of 5u over u. I know that x is really comfortable for us, but it doesn't necessarily have to be what we use every time. So here we are using u. Okay, so this is close to our special limit, but not exactly. Remember what we talked about, we need some consistency. We need this angle to match our denominator, okay? We have the first stipulation met where we're going towards 0. The special limit is not going to work unless we're going towards 0, okay? But we don't have these two matching. Well, what could we do to help us? If this denominator were a 5u, that would be a lot better. So let's multiply it by 5. But I can't just multiply the denominator by 5. We have to multiply by 1 so that we don't change the limit. So I'm going to multiply by 5 over 5. So we have the limit as u approaches 0 of sine of 5u times 5 all over 5u. Well, now this sine of 5u over 5u, as u approaches 0, we know that's going to go to 1 because that's our special limit. And now we have 1 times 5. I do need to see this work. We can't just say, oh, there's a 5 there, it must be 5. I need to see that you used that special limit, okay? All right, last example. Yep, last example. Okay, so we have the limit as theta approaches 0 of sine of 3 theta over sine of 5 theta. Okay, all right. Well, we know that the sine of 0 is 0, and the sine of 0 is 0. So this isn't great, but we're going to be able to do something algebraically, or in this case, trigonometrically. Now, For our special limit, it would be really cool if we had sine of 3 theta over 3 theta, because we do have theta approaches 0. Okay, so let's just make that happen. Let's go ahead and multiply by 3 theta over 3 theta. Okay, so what we have, and I'm going to go ahead and rearrange so I have things grouped together nicely. So I have the sine of 3 theta times 3 theta, and I'm going to rearrange our denominator so that 3 theta comes first, and then times sine of 5 theta. Okay, now we have our special limit. We're going towards 0, and we have sine of 3 theta over 3 theta. So we know that this limit right here goes to 1. And now we're left with the limit as theta approaches 0 of 3 theta over sine of 5 theta. Okay, well, we still aren't quite there, because we're still going to get this 0 over 0 business. And we have sine of 5 theta in the denominator. Man, it would be really nice if we had 5 theta in the numerator, right? Well, we have sine of 5 theta, and we have at least theta. If that 3 were a 5, that'd be a lot cooler. So let's just go ahead and make that happen. Let's multiply by 5 over 5. And then once again, I'm going to rearrange, okay? So we have the limit, it's probably not good to write on that line, huh? We have the limit as theta approaches 0 of, I'm going to write 5 theta times 3 in our numerator. Okay, I just rearranged those a little bit. And then in our denominator, we have sine of 5 theta times 5. All right, so we have our special limit. As theta approaches 0, we have our 5 theta over sine of 5 theta. We know that that is going to go to 1. And then we're just left with 3/5. Okay, so as a reminder, I could give you a homework quiz at any time. So make sure you're doing your homework so that you are ready for it. Okay, because you do get to use your homework for your homework quiz whenever that were to happen. Tonight you have a book assignment that covers these topics. Please make sure you use Calc Chat to check your